In this video, we're going to be taking a look at 4.2, which is titled Older and Faster, and we are going to look at negative correlations and what that looks like. This entire unit, we've been looking at different ways that variables can relate to each other. We've looked at different correlations. We've looked at linear, whether they relate to each other in a linear fashion, or inverse are the two big ways. And now we're going to look at what does a negative correlation mean. So first of all, our story for 4.2 is Magnolia Elementary is a school with students who are 5 to 14 years old. On field day, all students were timed in a 100-meter race. The table shows the data for some of the students. So here you have the student's age and then the race times. Okay. The graph below shows the data from the table and the line that it models. So you notice the student's age is down here. This is considered our x-axis. So this is your x-axis. And then the race time in seconds, that's considered your y-axis. So here are our x variables and there are our y variables. Okay, and most times the x is represented by the independent variable, and the y is your dependent, meaning the race times are going to depend on the student's age, and in this case that makes more sense to set it up that way. Big questions that we're going to try to answer. How would you describe the relationship between age and race time? Would you say the relationship is strong or weak? And then are the data points close to the line or are they spread out? So those, we can answer those kind of right now, but those are the three questions we're going to explore in this story about the field day at Magnolia Elementary. So part A, the line drawn on the graph models the relationship between age and race time. We're looking at that graph right there. Go ahead and answer numbers 1 through 4 to the best that you can, and then come back to the video, and then we'll go over the answers for 1 through 4. So pause the video and then come back. Okay, so to find the approximate slope of the line, remember that's rise over run. Number 1, if we're looking at the slope of this line, we know a few things. So number 1, we know that the slope is going to be negative, right? It's going to be a negative value because it goes down from left to right. Then if you want to use a couple points, you can use like this point and that point. And you can look up into the graph to determine what those points are. So this looks like it's about the age of 5 and 20 something. So look up here. So 522 is the first point that we're going to look at. 522. And the second one is going to be 1115. Make sure that's actually a point up here. 1115 right there. Now we're choosing those two because they look to be on that line. All right, now to find the slope, remember it's y minus y, so it's going to be 22 minus 15 over x minus x, so that's 5 minus 11. And when we do 22 minus 15, that gives us 7. 5 minus 11, that gives us about 6, negative 6. So our slope is about negative 7 over 6, or negative 1 and 1/6. I would rather keep it like this, so when we write our answer, it would be negative 7/6. If you have something around negative 1 point, what would this be? Negative 1.15, 1.2, 1.25, somewhere around there. Important part is that it's going to be negative. Okay, the second one, how does the slope help you understand the relationship between age and race time? So this negative slope indicates that as the student gets older, so here the student is getting older, the race time decreases. So that's what we would write here. As the student gets older, the race time is going to decrease. Okay? And then do you think it makes sense to predict a race time for a 7-year-old using this number line? I think that it would be, right, for a 7-year-old. If so, do you predict a 7-year-old? What do you predict for a 7-year-old? How confident are you in your prediction? So we could come right up here, and to predict for a 7-year-old, what we're going to do right here would be 7, and we come right up here, boom, and the race time is probably going to be around 18 seconds. That's our prediction for a 7-year-old. All right. Then how confident are you? I would say I'm pretty confident because there's a pretty strong correlation between the student's age and the race time in seconds. Of course, you're going to have those outliers who are either really fast or not so fast, but I'd be pretty confident that it'll be right around 18. And then number 4, do you think it makes sense to predict a race time for 21-year-old? Now, that's different, right? Because if you think about what happens beyond 16, right? Once you turn 16, that's probably about as fast, 16 to 18, about as fast as you're going to get. Unless you start training for the Olympics, you're not going to get much faster, but that's going to be extremely rare because 0.00001% of people, something like that, actually go to the Olympics. And so it'll be extremely rare for something like that to occur. So anything past 16 years old, I would not use this model, because if we were to draw that line would begin to level out and then start back up as you get old, like some of us. And if so, no, we can't predict it. I would say no, it's not a good prediction up past 16 to 18. Okay, on B, some data points are very close to the line while others are far from it. The points far from the line don't seem to fit the model. So go ahead and answer these. You're looking and kind of evaluating or thinking about those problems outside of the line. So that would be these problems or points out here. What do we know, or what can we assume or say about some of those? So go ahead and answer B, 1 through 3, and then come back and see how you did. Okay, in the first one, you want to find 2 points that don't seem to fit the model. What are their coordinates? So we come back up here, and we're finding 2 points that don't fit the model. So let me get rid of some of this stuff that may be a distraction to us. So 2 points that don't fit the model. There's several. I would say the ones that lie the most outside are probably that one and that one, right? And those 2 coordinates, the first one is going to be 10, 20. That is that one right there. And the other one is going to be, it looks like 13, maybe 16. That would be that one right there. So we wanted just 2 points that don't fit the model. Then 2, why do you think the points don't match the overall pattern? Explain and think about the relationship between the race time and age. So why do I think these points don't match the overall pattern? So if you look at it, these points, this 10 means that this student is 10 years old and they ran a race time of 20, right? Where on average, the race time should be right there for a 10-year-old, which is about 12 seconds. So this tells us that this person is slower than normal, or what should be considered normal. All right, and then the same is true for the second one, because here you have a 13-year-old that runs a 16 second time for your 100 meter, and so he or she is also slower than normal. Okay, so that was number 2. And number 3, remember back to the Vitruvian Man in 4.1, we used the height to arm span. So it was arm span is equal to the height, right? Where this was your x-axis and the arm span was your y. So it went something like this. So this was your height, and then your arm span was over here. okay? Now, it says a 6'9" basketball player has a 7'5" arm span. Would your data point fit that model? If you remember, our line was a slope of 1, meaning the ratio is 1 to 1. So if I'm 5 foot tall, my arm span is likely going to be 5 foot as well. So arm span and height should be equal to each other, according to Vitruvius, who studied different similarities of lengths in the body, right? But if you have an NBA player whose arm span is significantly higher, that point is going to be above that line. So that answer is part B. Would that plot be on or above? It would definitely be above. And to go back to part A, no, it really would not fit that model because it would be off of our line. And if you remember, our line that we had, all those points are pretty closely tied in together, but someone who's in the NBA is not going to be in that because their proportions are not what we would consider very normal. And then in part C, the table and graph show age and grade point average for 14 students again, we're at Magnolia, but this time we're at the high school. So we're going from ages 14 to 18. So down here are your ages, 14 to 18. And then the GPA goes from 0 to perfect of 4. Now go ahead and answer these questions about the comparison between age and GPA, and then pause the video, come back, and see how you did. Okay, number 1, the scatter plot. So our age and GPA strongly related for these students. So if we look at this scatter plot, there's really no correlation. The points are kind of all over the place. Right, I could either go this way, I could go that way. There's really no correlation between the two. So I would say on number 1, no, there's not a strong relationship between age and GPA. And then make sure you explain that, because on a lot of our tests and quizzes, we kind of have to explain why do we believe that no is our answer. Part 2, how is your story or your answer, part 1, supported by the table? So if you look at the table, look at this. So you have an 18-year-old with a 1.9 and a 18-year-old with a 3.0. That's kind of all over the place, right? So here you have an 18-year-old with a 1.9, 3.0, and you have a 14-year-old that's higher than both of those, and then you also have a 14-year-old that's lower, and a 15-year-old that's lower than all of them. So there's really no correlation here, even looking at the table. But looking at the table, it's a little harder to find. You could also, looking for some sort of relationship, well, I guess that wouldn't help either, because what you could do is kind of group these together. You're just grouping the ages together and looking at them that way to try to find, okay, do 14-year-olds tend to do better than 17-year-olds? But there's really no correlation there either. And then C, how is your answer to part 1 supported by the scatter plot? So the scatter plot, the picture representation of our story here, is much easier to determine questions like this. Because if you can see where all those points are in space, you can more easily see that there is no correlation. It would be something like that. There's definitely not a linear correlation, and it's not positive, it's not negative, because my graph could easily go up and to the right, it could go straight over. There's really no correlation. So when you're looking for correlations, it's a lot easier to look at the graph than it is the table. All right, that's all I have for you for 4.2, older and faster, looking at negative correlations.